Okay, let's take a look at these announcements here. I've just collected homework 4A. So that was some problems related to convective acceleration, streamline, streakline, pathline. And so now in homework 4B, which is due a week from today, we're going to be applying the ideas behind fluid acceleration. And today we're going to discuss Euler's equation, and then as we move forward, we're also going to hit the Bernoulli's equation. Before next Sunday's homework submission, though, you've got a quiz on Tuesday. And the quiz is going to cover material since the last midterm exam. And so the last midterm exam was chapter 2 and 3, and now we're in chapter 4. So the quiz will cover chapter 4 through and including today's lecture. But the safe bet is focusing on the material that you had included for the assignment you turned in today. All right, so those are the announcements. Any questions before we move into Euler's equation? All right, here it is, Euler's equation. Now, Euler's equation is the application of the idea of local acceleration. And do you remember in the last class period on Tuesday of last week, we talked about the two kinds of acceleration. Local acceleration is the one that probably most people are already familiar with because they learned about it in physics and other courses in the past. So that's local acceleration. And then what's the other kind of acceleration? Convective, right. So convective is what we'll refer back to when we're talking about Bernoulli's. But here for Euler's equation, the A that's listed here, A sub L, that's local acceleration. Now, L here doesn't stand for local. And I'm sorry that sometimes the letters of the alphabet are repeated, and that makes it a little more confusing to understand. But here, L is just referring to a certain direction. And here, dl is referring to an incremental distance between points. So if we look at this equation, what it's saying is that acceleration is going to affect the sum of two things. Acceleration is going to affect the sum of pressure and then gamma z. And you've seen this expression, pressure plus gamma z, in the past when we've discussed piezometric pressure, because P sub z, piezometric pressure, is the pressure at a location plus gamma z. And all that means is, for example, if we had a tank of water and we were comparing two locations and we wanted to compare how does the pressure change between 1 and 2, we sort of know that if you go down through the fluid, the pressure is increasing, but we'd be losing z at the same rate. So here, pressure plus gamma z, the application of piezometric pressure is that if you go between 2 points, from 1 to 2 inside of the tank, the sum of pressure plus gamma z will stay the same. Now that's under static conditions. If we have this tank of water and we're accelerating it, then things may be a little bit different. And so that's what Euler's equation is going to allow us to do, is it's going to allow us to look at some element of water that is experiencing a local acceleration, and then we'll look at how far apart 2 points are. That's what this dl is going to tell us, the distance between 2 points in a certain direction, in the direction that the acceleration occurs. And then, of course, the fluid that we're working with will have a certain density. And then this expression in here will allow us to keep track of the change in pressure plus gamma z between the 2 points. And so in the formula sheet I give you for midterm exam 2, this is the formula I'll provide. This is Euler's equation. But what you're going to want to know how to do is transform this equation into the format of it that we usually use for problem solving. And so what you'll do is you'll in your mind say, let's assume, for simplicity, that there's a linear variation of pressure plus gamma z. And so in the case that the variation is linear, then we're just going to replace this del with a delta, saying that between the 2 points the change is linear. And then more specifically, we'll say, let's take these 2 points and call them location 1 and location 2. Now here's a really important note. In terms of sign convention, you're going to need to keep track of what is 1 and what is 2. We mean something specific here, and you'll notice that there's a negative sign on this side, on the right side of the equation, and I'm going to explain why we have that negative sign in just a moment. But to begin with, I'm just going to warn you that these two locations may not be interchangeable, and so there's a rule for what you call location 1 and what you call location 2, and I'll show you that rule in just a minute. But what this is saying is that between 2 points, the sum of the pressure plus gamma z, so the piezometric pressure between location 1 and location 2, is affected by how far apart they are, the density of the fluid, and then the acceleration. And I've just sort of expanded Euler's equation for an acceleration in the x direction. And so you'll notice that now I've replaced L, which was just some generic direction. Now I'm saying, let's apply this equation in the horizontal plane. And so what we'd want to know, in this case, how far apart is 1 and 2? So x direction, this is the delta x between 1 and 2 that we'd be interested in if the tank was accelerating to the right. We'd want to know how far apart are they horizontally. Now we don't ignore their vertical distance between the 2 points, because you'll notice that we have z in the left side of Euler's equation, and so z2, z1. So we are going to be keeping track of the elevation in the fluid of the 2 points, but we're also going to be looking at how far apart they are sideways, because it's the sideways direction that the acceleration occurs. So this is a lot of stuff. This is one of the big ideas of the semester. And this is why you're paying the big tuition bucks, is to learn big ideas like this. And so what questions have you got so far about Euler's equation? All right, well, as the questions approach, don't feel hesitant to interrupt, because this is a really important idea. And so here's a little bit about the sign convention. The reason why I labeled this location 2 and this location 1 is because if we are accelerating to the right, of the 2 points, one of them has more x, meaning it's further to the right, and one of them has less x, meaning that it's further to the left. And so our notation system we're going to use is that location 2 means the one that has either more x if we're accelerating in the x direction, or if we're considering a vertical acceleration, then location 2 is the one that has more z. So more elevation if you're accelerating vertically. In this example I've just drawn on the board, we're accelerating horizontally, and so this is we're starting to measure x as we move rightward, and so location 2 is further to the right, and that's why we called it location 2, is just because it has more x. And then what that means is that our acceleration is going to have a directionality to it. So we would put a negative number if the fluid is accelerating to the left, and if it's accelerating to the right, then that will be a positive acceleration. All right, so now with this negative sign, let's think about why is there a negative sign there. So take, for instance, this tank of water that I've drawn on the board. It's accelerating to the right. Now remember when we were talking before, we had the idea of if you're standing in an elevator and the elevator's accelerating upwards, you feel more pressure on your feet. In the same way that if you're watching a movie with an astronaut who is being blasted into outer space, it's like pushing them into the seat. And so what we know is that the pressure is increasing in the opposite direction of the acceleration. So let me point what I mean. If the tank is accelerating that way, then the pressure is higher in that direction. It's just like when you're sitting in a car. If you're in a car that's accelerating very quickly, your car is accelerating forward and you are being pushed backwards. And so this negative sign is a way of us enforcing that phenomenon in the equation. It's a way of saying that we're going to have more pressure at 1 when we accelerate to the right. So the pressure is decreasing in the direction of acceleration. So if you're taking notes, circle that negative sign and just write a note to yourself, pressure decreases in the direction of acceleration. And then that'll remind you why that negative sign has to be there. All right. So those are all the moving parts in Euler's equation as we expand it out to solve problems when we assume a linear variation, and we will through all of the problems for the semester. So I want to show you some applications. I've got 3 examples we're going to take a look at during today's class. One I'm just going to do on the board while you watch, and then the other 2 I'm hoping that we'll have enough time for you to get a chance to try out Euler's equation. And as always, please interrupt me if you've got any questions. So for this first example, we're going to say, let's use Euler's equation, and there's water flowing through a pipe. And the water is accelerating as it moves to the right. Now this isn't a convective acceleration. Remember when we were talking about the nozzle in a previous class, in this case it was a convective acceleration. Why was it a convective acceleration here? What caused the acceleration as the water was flowing through that physical device? The cross-sectional area is decreasing, and so the water had to speed up to get through. Right, so that's convective acceleration. This isn't. The pipe walls are parallel here, and so the fluid is not changing with respect to position, and that's the definition of convective acceleration. So if it says it's accelerating to the right, we can tell just by looking that's a local acceleration. And so what the local acceleration is caused by is unsteady flow. So someone, maybe at a valve or a pump upstream, they're opening the valve so more and more water is going through that pipe. And so the flow rate is increasing, and that's what's causing the acceleration. The velocity through the pipe is increasing over time. So this is a local acceleration. So because it's a local acceleration, that's why we're applying Euler's equation here. So what it's saying is, let's say that the acceleration we observe is 6 meters per second squared. And we've got a couple of location A and location B. And there is a phrase here, what pressure gradient is needed to accelerate the water at this rate of 6 meters per second squared. And pressure gradient, that phrase means something specific. What it means is the change in pressure per meter of length of pipe. And so pressure gradient, let me write it on the board here, pressure gradient. They're talking about what is the delta P divided by the delta X. So the acceleration is in the horizontal plane, so we're going to be applying Euler's equation in the X direction here. And so they're asking basically, if A and B are 1 meter apart, how much pressure difference is there between the 2 points? What is the delta P divided by delta X? And the easiest way for us to answer that is we're going to say some change of pressure in terms of like pascals per meter. So how much different is the pressure at B versus A? And what we should expect, just based on our anticipation, is we would expect the pressure to be higher at which location, at A or at B, if it's flowing to the right? Yeah, the pressure is going to be higher at A because remember, the high pressure pushes the water to the right. So the water will be flowing from high pressure towards low pressure. So when we do these calculations, in our mind we should be saying, does the numbers match the logic of what we expect? Hopefully it will. All right, so the first thing we do is expand Euler's equation. That form of the equation, we can't start substituting in directly yet. We have to say here, as our first thing, the L direction is x, because it's accelerating in the right. So what we're going to do to expand out Euler's equation is P plus gamma z at location 2 minus P plus gamma z at location 1 is equal to negative delta x, density of the fluid, and acceleration in x. Okay, so far so good. Now we need to label our locations like what is 2 and what is 1. Do you remember we said that you can't use it interchangeably? Like there is sort of a rule on how we label those. And so what is 2? Remember 2 is whatever has the most x. We're in the x direction, and so location B is furthest to the right. That's what I mean by the most x, is it's furthest to the right. So location 2 is B, and then location 1 is going to be A. So if we do the substitution, now I'm going to remove that 2 and I'm going to put in the letters. What that means is we're going to have the pressure at B plus gamma ZB minus the pressure at A minus gamma ZA is equal to negative delta x times the density times the acceleration in x. And you'll notice I distributed that negative sign there, so it's negative pressure at A minus the gamma ZA. Yes? Right. Good question. So let's say her question is, what if the acceleration is to the left? Well, location B would still have more x, and so we'd still call this 2, and this would still be 1, but we would, if the acceleration is in the opposite direction, we'd put a negative sign for the acceleration when we write the number into a sub x. Good question. And that would handle the acceleration in the opposite direction. All right. So how are the elevations different? Because we've got a z sub b term, a z sub a. Yeah, they have the same z. And so over here I'm going to write zb equals za. And doing that allows me to just cancel both of these terms out directly. So what I'm left with is p sub b minus pa is equal to negative delta x density acceleration in x. So already it's starting to look pretty good. Like, I know it's asking what is the pressure gradient. I just want to have delta p divided by delta x. And so in one more step I can rearrange this equation to look like the delta p divided by delta x that I'm hoping for. So let me do that. So this leads me to delta p. By delta p I mean the pressure at B minus the pressure at A. Divided by delta x is going to be negative the density of the fluid times the acceleration in x. So now let's finally substitute in some numbers. We've got the negative sign still there. I don't want to accidentally lose that. The density of the fluid, what did it say this is? Water. So I'm just going to use 1,000 kilograms per cubic meter, right? And now the acceleration. Now it's to the right, so it'll be a positive value, 6 meters per second squared. And again, that's a local acceleration, which is the whole reason we're doing Euler's equation. So the pressure change is going to be negative 6,000. Now what are the units? Kilograms, meters per second squared, divided by meter cubed. Okay, now a kilogram meter per second squared, that's a Newton. So that's like saying negative 6,000 newtons per meter cubed. And we want the units to be, for a pressure gradient, Pascal, which is newtons per meter squared, divided by meter. So did the units match up so far? Yeah, newtons per meter squared divided by meter, that's going to be like the same as newtons per meter cubed, right? Which is what we've got. So we can rearrange and write this as negative 6,000 pascals per meter. And that will be our final answer. Let me bring that up on the screen so that it's included in the lecture video. Okay. All right, so this is accelerating to the right, and remember, what was our logical guess? The pressure would be decreasing in the direction of flow. And that's why we've got this negative 6,000 pascals per meter. So the fluid is accelerating to the right because the water is rushing towards that location of lower pressure. Now let me just give you a warning. So far in the semester, we haven't talked about how to quantify pressure changes due to pipe friction. I mean, we've identified it as a concept. We know it's out there, but it's not till chapter 7 that we're going to start accounting for it. So here, this problem, the pressure change isn't because of pipe friction. This is just we're talking about the effect of acceleration. And so if we were going to account for frictional losses, then the pressure change would be even greater than this. But this is just the relationship between the acceleration and the pressure change that we've quantified so far. All right. So, any questions for this illustration? All right. Well, Euler's equation is really interesting, and it can be applied so many different ways. Let's take a look at this enclosed tank. This is the first problem on the handout that I've given you. And we've got a tank where the liquid inside of here is mercury, 13.56. I accidentally didn't include the 6 here. So 13.56 is the specific gravity of mercury. And it's accelerating in two directions. So let's look at this. A sub x is 15. That means it's accelerating to the right. A sub z is negative 12.5. So what does that mean? It's accelerating down. Now, we're going to start using z rather than y to talk about vertical distances. Here in Euler's equation, it's using z to talk about elevation. And so the way that we're going to handle this problem is you consider each acceleration separately. And every single semester I teach this class, and I've taught it more than a dozen times, someone tries to combine both accelerations together and solve it in one step. Don't combine the accelerations. You have to consider the horizontal acceleration in one part of the problem and the vertical acceleration in another part of the problem. Keeping them separate is the only way to get the right answer consistently. So, all right, here we know the pressure at one location. We know the pressure at the edge here, G, and we know the pressure here, H. And so, first of all, it's accelerating to the right. Does the pressures that are mentioned match what we'd expect for it being accelerating to the right for 15 meters per second squared? The pressure is higher at G, and so that is logical for us. Because remember what we said is that if it's accelerating to the right, then the pressure increase will be to the left. That's that negative sign working its way in. So, or in other words, the acceleration, the pressure increase is in the opposite direction of acceleration. So it accelerates to the right, the pressure is higher on the left. And so that's what the P sub G and the P sub H are telling us. What we don't know is the delta this delta x. So you're going to apply Euler's equation in the x direction, and delta x will be our only unknown for the horizontal axis. And then for the vertical axis, we know the distance, so the 0.87 meters is what we'll use for the delta z, and we know the vertical acceleration. But what we don't know is what's the pressure at F. Now let's think about logic. Will the pressure at F be higher or lower than the pressure at G? What would you expect? Lower? If it wasn't accelerating, we'd expect it to be lower, right?
Depending, maybe it's lower.
Why does somebody say it's going to be higher?
Because it's the furthest to where the acceleration is.
Okay, all right. Opposite direction. So it's accelerating down at 12.5. What if it was accelerating down at 9.81? Then the pressure between G and F would be the same. There would be no pressure variation. So if it's accelerating down at less than G, then what we normally expect we will see. We would see higher pressure at G and lower pressure at F. But here it's accelerating down faster than G. So actually what we should expect is to see more pressure at F than there is at G.
So here it's mercury.
It's mercury, so
Pressure for like 0.5 meters is going to be way higher, like increase in pressure.
the pressure differences we're going to see will be much larger than they would with water. But the effect is still the same, that there will be more pressure at F than there will at G. All right. So what I'm going to do is I'm going to bring up the lights. I'm going to stop talking so you can start working and collaborating with your classmates. Find these two things. Find the pressure at F, find the delta x, and keep track of the location 2 and the location 1. Be careful about that, and also be careful about the sign that you put into the acceleration term, whether it's positive or negative.
the elevation at point F is 0 or the elevation at point G is 0?
Well, F will be 0.87 and G will be 0. Yeah. And remember that the density here is going to be 13,560 because it's mercury, so it won't just be 1,000. And yeah, you made the conversion here, but also it needs it for that one. Okay, let's talk through this solution a little bit here. So this one's tricky because it's accelerating down and it's also accelerating to the right. So what we do is we just take those two different accelerations and treat them completely separately. It's as though this is two separate problems. So first, if we want to find the pressure at F, we're talking about the vertical acceleration. And for now, we'll ignore location H. So in the vertical direction, we know one location and the other location is unknown. What we will expect is that the pressure at F will be higher than the pressure at G because this is accelerating down faster than 9.81 meters per second squared. That's sort of the logic that we want to keep in mind when we double check our solution to make sure it's reasonable. So let's start with writing the equation the full way. Now let me make you a warning to you. There's a hidden landmine here. If you don't write the full equation, then it's so easy to make mistakes because there's so much that you have to get everything exactly right. You have to get the location 1 versus location 2 exactly right. You have to get exactly right the sign of the acceleration. So here it really pays to be meticulous and write everything out, including the units, because if you accidentally write the pressure in kPa instead of pascals, there's just a lot happening here. And so I'll encourage you to be as detailed and expansive in your solution as you can. So here I've written, first of all, expanding out Euler's equation in the z direction. So here I've put delta z in place of delta L, and here I've written z for our acceleration direction. Okay, what's location 2 and what's location 1? F is above G, and so F has more z. So we're going to identify location F as our upper one and location G as the lower one. And now I'm just rearranging the equation in terms of the unknown. P sub F is what I'm trying to solve for. And so Z sub G and Z sub F, what I'm saying is let's have the elevation at G be equal to 0, and then F will be 0.87 above that. So when I start doing the substitutions here, you'll notice that this whole term of gamma ZG, that simplifies down to 0 because I'm just saying let's have that be our elevation datum. And then here I've got the unit weight of mercury multiplied by the elevation at F. Now here the ZG is going to be the same as delta Z because that's how far above location G location F is. So here I'm seeing the 0.87 again. And then I have to make sure that I'm using the unit weight, the density of the fluid and not the gamma again, because in the equation sometimes I'll be writing the gamma of the fluid and sometimes I'll be writing the density of the fluid. And finally the acceleration is negative 12.5 because it's accelerating down. So here is the 485, which is the original pressure at G, and then look at these two different components. This first part takes into account the fact that the hydrostatic effect, the negative 115, that's because of the elevation difference. And then the 147 is because of the acceleration. So here what you see is that the acceleration down is a bigger pressure change than the normal hydrostatic effect of gravity. There's two accelerations in the vertical plane. There's gravitational acceleration, which causes this pressure change. And then there's the physical acceleration downward of 12.5, which causes the 147 pressure increase. So when you combine the two together, you get 516 kPa will be the pressure at F. All right. These are really a matter of practice. And so if you struggled with the first problem here, don't feel discouraged. You'll get it. All right, now the pressure difference, the elevation difference, how far apart G and H are. Here you can see the solution on the board. The first step is to call H2. Guys, cool it. All right. Location G is 1 because it was further to the left. And here's 1, here's 2. The elevations are the same, so I'm saying ZH equals ZG. And so the pressure difference is equal to the negative delta x, density, the acceleration in x, and I'm going to have a positive value that time. So just rearranging for the delta x, 1.8 meters approximately is how far apart they would have to be for that pressure difference. All right, so if you need to consult the solution again, it'll be in the recording that's posted on YouTube. Let's look at one other thing that Euler's equation allows us to look at. Think about a tank that's open. This one that we've just been looking at, this was an enclosed tank, and so it's full of liquid to the very top of the tank. What if it's a bucket of water? And maybe you've noticed sometime if you're carrying a cup of soup or a glass of water that's full to the top, why do you have to walk so carefully when you have a bowl of soup that's all the way to the top? Because if you move too quickly, the soup will splash out of the container. It's because Euler's equation tells us that during acceleration, the liquid surface is going to increase in the opposite direction of our acceleration. So look at this tank here on the right. What this is showing is that there's a before and an after. Before, there was no acceleration to the right, and the liquid was level. But then suddenly we started to accelerate rightward, and what happened is that the liquid level increases on the left side and it goes down on the right side. So Euler's equation can tell us how much of an elevation difference we should expect. And so if we accelerate the tank to the right, the fluid level increases on the left side. And Euler's equation describes that because here in the middle of Euler's equation, it's the pressure plus gamma z. And so it's either the pressure that's going to change or the liquid surface level that will be described by z. And in fact, if the z is changing, then the pressure on the bottom is also going to be different. There would be more pressure on the bottom of the tank at D because there's more liquid above it if we're accelerating it to the right. The pressure variation on the bottom of the tank, if you look at it, here at C, when it's accelerating to the right, there's not very much liquid above it, and so there would be less pressure at C than there is at D as we accelerate the fluid to the right. So one of the tricks of this is if you know how much it's accelerating to the right, a sub x, that would be like a horizontal acceleration, you can predict the angle that this is going to make, alpha, the angle with the horizontal. And so if you're accelerating to the right at 9.81 meters per second squared, then that angle would be 45 degrees. It would be sideways because the tangent of 1, 45 degrees is how you'd find the angle if you're accelerating to the right. So depending on how much accelerating, you can know what the angle of the liquid surface is going to be. Now, I don't think we're going to have enough time to go through this example in detail, but let me just show you what I had in mind for this example. So we have a tanker truck that's open to the atmosphere. And there's a liquid in here. It's, I think in the example, I'd intended the liquid to be water. And what we know about this truck is if it's 18 feet long, 7 feet is the total height of the tank, and then the truck is never going to accelerate or decelerate more than 8.02 feet per second squared, then we can predict the angle, and that would tell you how high the liquid level can be. So we're just using Euler's equation to predict how much of a slant is going to be on the liquid surface based on the acceleration, and then if it's slanting a lot, then that means you can't put as much liquid in it because then it would start to spill out of the truck. So let me just show you the solution. Problems like these are less common than the enclosed tank type problems. But in any ways, it's kind of an interesting problem here because what you'll see is if we're given a rightward acceleration, 8.02 feet per second squared, then you can find the angle there, 14 degrees, using the tangent function. And then you can see that there's triangles here. There's a triangle where if the truck is 18 feet long, then that means that this length at the top of the triangle is 9 feet. And we would want to find h, which is this distance from the original water surface down to the water surface when it's accelerating, because that same distance h is going to be this h as well. So it tells you how high above the water surface it's going to be going up when the truck is accelerating. So then once you found that height, it would tell you the allowable liquid depth would be 4.76, because if it was any more full than that, there was more water, then when it accelerates, as it starts to slant, then it would go out of the truck. So, there's a lot of geometry backflips in this problem that I don't think is necessarily the heart of the issue. The heart of the issue is that Euler's equation predicts not just pressure changes, but elevation changes as well. So that you can look at a fluid that's open to the atmosphere, and as it's accelerating, you can know how that surface is changing, and you could, like pick a distance that the 2 points are apart and find out what is the delta z. All right, so when we get together in class on Tuesday, we're going to start to talk about Bernoulli's equation, which arises out of our convective acceleration definition, but we'll do that after a brief quiz at the beginning of class. All right, so have a great day. I will see you on Tuesday.